Hello everyone. So today I would be presenting how we can simplify mathematically how the large language models work. So I'm Vikram Agnihotri. When I want to find out that how we can actually do a simple mathematical calculation to find out about how large language models work, I could not find anything on the topic. That's when I actually will delve deeper into this particular thing and find out how we can actually determine how the large language models work mathematically. So for this, we are taking a very basic example. We actually have to find out New Delhi is the capital of, and we'll be predicting the last word, which is India. We'll be taking this particular example and showcasing how does a large language model work. A real LLM is much more complex than what we'll be presenting in uh, this particular presentation. But what we want to showcase is that the context or the idea behind how large language models is same. So this particular video would be divided into two sections where the first section will be taking a simple calculation and the second section will be taking how the various important caveats behind how the large language models work, such as the attention mechanism, etc. We'll be talking about those particular things in the next. But this one will dare open the minimum boards and talk about this particular thing. What we actually have to do is, firstly, whatever sentence we take over here is actually splitting the text into tokens and then turning these tokens into vectors. The third is combining context behind this. The fourth is predicting the next token. The fifth is measuring the error. And the sixth is back propagate the gradients to improve the weights. So these are the six steps that we follow when we actually have to find out how the working of prediction of the word India when these five words are fed into the model. New Delhi is the capital of is fed into the model. How can we find out that India is the right word that actually has to fit over here? And we are taking a very small example over here, but the example can be very, very profound if you would want to go ahead and find about how large language models work. Now, what we'll be doing over here is, well, the first step is tokenizing the sentence. Now, what do we mean by tokenization? Tokenization means that we are actually breaking this particular sentence down into some particular numbers. Now, computers understand the numbers very well. And we're just taking a basic example over here. New Delhi is broken as two separate words, is the two separate words, capital of and India separate words. But if you will see how the chat GPTs of the world's work, sometimes New and Delhi might be the same, might be taken into the same embedding that they will be taking. There will be just one embedding vector that will be created. And sometimes a particular word, for example, capitalized can be broken into capital and sized, etc., etc. So that's how the embeddings work. Embedding is just basically converting the textual information, which is in string, basically some number format. That's what it means by creating the text into tokens. So now we are just converting into a two-dimensional token. So what we are doing is new can be represented by zero point 0.2 and zero point 0.1, Delhi by zero point 0.4 and zero point 0.2, and so on and so forth. We have taken various tokens over here. And based on these particular tokens, we are wanting to find out what is the next token over here. Another important thing to be noted over here is that whenever we are talking about all these sorts of things, what we are trying to do over here is we are just taking a two-dimensional space over here, and we are actually placing the words new. Let's say new we are placing over here, Delhi we are placing over here, is we are placing somewhere over here, and so on and so forth. So we are actually placing these words over here, and these words represent these particular vectors from 0, comma 0 to these particular lines are the various words that have been represented over here in the two-dimensional vector space. Similarly, the chat GPTs of the world take a very higher dimensional vector space and put these words into these n-dimensional vector space that they would be having and try to place the words over here. And what we actually have to do is when we try to provide the context about this particular model, for example, we are saying that good word is placed over here. Let's say this is good. Okay. So if we are placing good over here, we also want to place, let's say, uh, excellent. So we would want to place good and excellent somewhere between. I'm not very good with the writing over here, but we would want to place good and excellent somewhere in conjunction to each other so that it can be. So, for example, when we say a particular thing is good and a particular thing is excellent, that means both the things talks about the positive thing about a particular thing. So these two words would be placed in the same place in the two-dimensional vector space. So what we are doing over here is we are converting this entire sequence of sentence, New Delhi is the capital of India, into this two-dimensional vector space, which we have given over here. And these are just indicative embeddings. The embedding in real world can be very complex in nature, but we are actually taking a small example and showcasing how it would run. Now moving on to the next bit, we see that we create a context vector. Context vector means there are multiple things that the context vector means, but context vector means that we are actually placing these particular sentences somewhere and trying to contextualize the sentence. What does New Delhi is the capital of mean? And there are various ways in which we provide the context. We actually have to provide the context like what is each word meaning with the other words. I mean, what does a particular word symbolize with the other word? Where does it reference? What does the grammatical mean, etc., etc. We take those particular English constructs into the place and convert it into a context vector. Now, we are not going in this particular video, we're not going into the nitty-gritties of what does the contextual, like how can we can provide more context to a particular embedding. We would be converting that, we would be providing that in the second video. But over here, what we're doing is we're actually taking all the sum of the first coordinates and sum of the second coordinates, and we are just taking an average of those particular embeddings to create the context. But in the real world example, there are there are various K, V, and other factors in place which will be seeing in the next chapter, how we can actually utilize these and get it the embeddings for this. So what we're doing over here is for this particular example, we're just taking the first coordinates and the second coordinates and just taking a summation of those and averaging this to provide the context. So what we're doing over here is that the entire New Delhi is the capital of is somewhere point 2 would be over here and 0.283 would be here. So we have said this can be represented by this particular point, which is 0.2, comma 0.283. It's somewhere over here that we are actually representing this particular point. So this provides the context that this is what we have. This is where New Delhi is the capital of lying in this particular example. But in real world, it's quite complex. But let's suppose for this particular topic, we'll just assume that this is the context vector that we have created. Now, moving on, we actually have to find out the next token. And we are just taking, and we have three particular tokens that can actually be taken into account when we're actually predicting the next token. It can be India, France, and Japan. We've just taken a very simple input for those particular matrices. And what we've actually assumed is that we have a formula which is weights into the context vector, which is H, plus some biases. That is how we are using this particular formula, which seems like a linear formula. We have a linear layer to actually predict what is the actual prediction for the next token. And based on this, we have actually taken what happens is we take randomized weights in the beginning and randomized biases in the beginning. So these are the randomized weights and the randomized biases that we have taken. And we create this Z or the linear layer to find out to predict the next token. What we are doing is this is a matrix multiplication. So we had zero point 0.2 and 0.2883 over here as the H vector. So we're multiplying 1 into zero point 0.2, 1.2 into 0.2283, and we are finding out plus the bias, which is 0.01, and finding out that for the word India, The, the value that we have found is 0.64. For the value France, again, we are multiplying this with H, which is zero point 0.2 and 0.2883. We are getting this particular thing. And for Japan, we are getting these particular things. So these were the weights for India, France, and Japan simultaneously. We multiplied these with the context vector that we had zero point 0.2 and 0.2883 that we found out by just doing the averagings. And we found out that India has a 0.64, France has this much, and Japan has this much. Though India has the highest higher logits, that means the probability of India being chosen as the next token is higher, but we can actually improve this further. And how we would do it, we'll just find out in the next example. Now, what we do in the next example is we find out the probabilities. Now, we have actually found the logit function, and the probabilities for what we need to project as we can find out e raised to power z1, which is 0.64 that we found out for India, the z1 score, divided by e raised to power z1, which is 0.64 by this by and this. We add these three and get the probability for India, which is 0.491, probability of France is 0.262, probability of Japan is 0.247. Though the probability of India is 49.1%, with the confidence we can say we are predicting the word India with a 49.1% confidence interval. But what happens actually is something called as a back propagation. Now, what does back propagation means? That we can actually change the weights and biases to make this probability even higher so that the loss function is reduced to the minimal value possible. And that's what we'll see in the next example. Now, what we're doing over here is we're finding out the cross entropy or the loss function is minus log probability of India, which is minus log 0.491, or the probability of finding India, which is 0.711. That is the loss function that we have found. Lower loss is the better, but over here we have a higher loss for India, which is not good. And we need to reduce this particular loss as much as possible. And to reduce this particular log, what we will be doing is we have dou L by dou Z is equal to P minus Y. That means we are trying to reduce the loss function with the, we are trying to reduce, so I'll just take it in this particular manner, that our function H is basically a function, is basically governed by X or the input vector that we had given. And H is actually the one which is governing the Z over here. And Z is the one which is actually governing the loss function over here. So the input vector is actually governing the context vector, which is actually governing the logits factor, which is actually governing the loss function over here. These are all how the loss function is converted. And what we are doing over here is to reduce the loss, we are doing back propagation. We are trying to reduce the we're trying to find the minimal for the z, and z is in fact related with the context vector, and the context vector is related with the input parameter. We cannot change the input parameters, but what we're trying to reduce is we're trying to reduce the weight w that we had and the bias b that we had. We'll try to do the back propagation and try to reduce weights and biases. So what we can assume over here is weights and biases are the knobs of a television. For example, you would have seen previous televisions which had those knobs based on which you could actually fine tune the picture. Similarly, we use back propagation to actually fine tune those weights and knobs to make this loss function as low as possible so that we can predict that by higher confidence we are getting India as the right value rather than France or Japan. That's what we are trying to do over here. Now, to do that, what we're doing over here is we are doing dou L by dou Z, which is P minus Y. Y is basically the hot true label. So what we have done is we have said the probability of India should be 1 or 100%. For others, France and Japan, the probability of those should be 0. So we are taking the probability function that we have found out, 0.491 and 0.262 and 0.247, and we are actually negating it with the actual value that we had for this particular for the actual vector, how it should be, which is 100% for India, 0% for France, and 0% for Japan. And this gives us dou L by dou Z should be equal to minus 0.509, 0.262, and 0.247. That is a loss function that we have got over here. And we need to utilize this particular function to reduce the back propagation. Now, what we do over here is we take Z or the logic function was basically weight into the context vector plus the biases. Now, what we are doing over here is we're doing a back propagation. To reduce the loss function, we are actually we are finding the gradient of the Z function, and Z is in turn dependent on weights and biases. So what's happening over here is if we actually have to put this particular equation, so if we take Z equal to weights into H, right? Or the context vector. If we have to find out how does weight W is a function of, if we actually multiply, if you would know some matrix multiplication, if we multiply this by H transpose, H into H transpose is 1. So if we multiply this by H transpose and if we multiply Z by H transpose, this would be equal to 1. So what we are doing is W is equal to Z into H transpose. You have multiplied both sides by H transpose. So H transpose into H or the context vector becomes 1 and Z into H transpose becomes Z into H transpose. Now if we try to take dou L, which is the loss function, and if we try to reduce dou L, if you try to find the minima or the local gradient minima of this weight function, we actually have to reduce the reduce the weights to actually reduce the loss function. We'll do dou L by dou W, or finding the minima for the weight. We are actually doing dou L by dou Z. We are actually taking this particular thing and then we are actually multiplying it by H transpose to get this particular equation in place. So if you would find the partial derivatives, if you would know about partial derivatives, then you would know we are actually finding out that because loss was a function which was governed by this logic function, and logic function in turn was governed by weights and the biases, and we are removing the biases and we are finding out how we can reduce the weights or actually fine tune the weights or find a local minima for the weights so that we reduce the loss. So that's how we get this particular thing. And what we have to do over here is we are multiplying, and the second equation is dou L by dou B or dou bias is equal to dou L by dou Z. How we are getting this is we are actually multiplying this particular thing dou L by by dou B. We are getting dou L by dou Z, uh, and why we are getting this is because we are now saying weights into context vector would be minimum, and we are multiplying this factor and this factor by dou Z, and we're getting the results. So that's what we're doing over here. So now what we are doing is gradient for India row is minus 0.509 into zero point 0.2, which is the context vector that we had over here, and minus 0.509 into 0.2883, which was the actual context vector, and we find out that this is the actual gradient for the India row. Similarly, gradient for the France row and gradient for Japan. And dou L by dou W is basically this particular metric and this particular metric. And dou L by dou B is basically minus 0.509, 0.262, and 0.247, which is equal to dou L by dou Z, which is this particular metric that we have found out over here. So that's how we do the back propagation to fine tune the weights and the gradients of the matrices. Because, now I'm just repeating it again, because loss function was actually governed by what was the basic function or the logic function used to find out predict the actual word. And that particular thing was dependent on the weights and the biases. Hence, we are actually fine tuning the weights and the biases so that the probability of the India should improve the best. And we are doing that by actually giving it that loss is the maximum currently on a higher side for India, and we need to reduce that particular loss. That's what we're doing over here. Next, we move on to back propagation to actually convert the context vector, which is the edge that we have over here, and we try to reduce that. And how we would do that is dou L, we are actually trying to reduce the loss function over here, loss function, by actually having a partial derivative of the context vector. And if you would see over here, that actual vector was we could actually find out dou L by dou H was basically weight transpose. So what we are doing over here is, so if we see over here, so weight into H is equal to the Z function, right? And now we are, and Z was actually, Z or basically the logit function, which was actually trying to find the loss, and this was actually governing the loss. And now we are actually trying to find out dou L by dou H, dou L by dou H is equal to, if we find out, we actually are finding the partial derivative of H. So if we take it to air, H is equal to, we'll multiply both these things by weight transpose, weight transpose. So weight transpose into weight is 1. So this gives H over here on this particular side. And the other side also will multiply Z by weight transpose. So we'll get H is equal to Z times weight transpose, or basically the logic times weight transpose. And now we can do dou H by dou L by dou H over here. And this is equal to dou L by dou, I'll put L over here, dou L by dou Z is equal to this into weight transpose. We get this particular thing, and now we are actually multiplying dou L by dou H. This is equal to the context vector. This is the context vector that we have. This is basically the dou L by dou Z that we had find out. And this is basically the weight transpose vector, the weights that we had taken, 1.2 and minus 0.3, 1.2 minus 1 and zero point 0.4. We are taking the weights over here and the dou L by dou Z, which are these values that we have over here. We multiply these and find out first coordinate is minus 0.538. The second coordinate is minus 0.532. And these are the two coordinates that we have. And now what we are doing over here is, because we use an average, so we'll take all the x1, x2, x3, and we'll again, because h in turn is a function of x, and how we had calculated h, we had actually taken a summation of all x1s to x6, or all the values of all the tokens, and divided by 6, or just take an average. What we'll do L by dou x1, we're trying to reduce the loss function with x1, and this is just 1/6 of dou L by dou h. And we just take whatever we had found on dou L by dou h, we just take 1/6 of this, and this is this particular vector. So we get this. We have actually moved backwards, back propagation, to fine tune the weights and biases and the context vector, so that we could actually find out that the right word or the loss for the right word should be the minimum, so that we get India in all the probabilities. Now, once we do this, we actually do one particular update. Now, what we are doing over here is, we are actually using the gradient descent algorithm. Now, what does gradient descent means? So, for example, if we plot all the weights over here, and let's say weights assume this particular shape, and all the biases over here, and let's say biases, we are actually taking multiple biases because we actually took it randomly. Let's say we started with over this particular point, and for biases, we started with this particular point. Now, this would talk about that we actually have to go in this particular direction for the biases, and in this particular direction for the weights. And if we go to this particular minima, which is this particular point, we would be at a minima where the weights would be rightly measured and loss function would be the minimum over here. Because at this particular point of time, dou L by dou W is equal to 0. So we try to reach this particular maxima. Similarly, we try to reach this particular maximum over minimum over. Sorry, we try to reach this particular minimum over here. And when we reach these particular minimas, we can actually be ensured that our loss function is the minimum. So that's what we are trying to do. Eta is basically what step we are going forward. We can actually take bigger steps toward this minimum, or we can take smaller steps. So this eta says how many steps that we take. We are taking a learning rate of zero point 0.1, but it can be 1, 2, etc., or very small like 0.01. If we want to take smaller steps, now how this particular gradient descent happens is when we are very close to the minimum, we take smaller steps, and when we are quite far off from the minimum, we take bigger steps. So you can actually find out about more about the gradient descent when we take other things, but this is basically how the gradient descent works. Now what we're doing is we're taking the weights, we are negating it with the eta, which is zero point 0.1 function, and taking dou L by dou W to actually reduce it. So the new weights that we have found out are these particular things. And similarly, the new biases, we can actually say B minus zero point 0.1 into dou L by dou B, so that we are actually taking the gradient at that particular point and moving towards the local minimum, and we find these particular things. Now we have updated the weights, now we have updated the biases, and with these particular biases, we will again go back, find out the context vector, find out the logit function, find out the loss function, and then do again the back propagation so that we find the minima and the loss is the minima. And that's how we can actually ensure that whenever we ask the question, New Delhi is the capital of India, should be given the maximum possible probability and should go on the top. So that's what it does. That's what we saw in this particular example. So the real LLM does not take average embeddings. It uses token embeddings, positional embeddings, many layers of self-attention, and feed-forward layers and layer normalization, which we will be covering in the back in the next section, in the next video. But training logic is the same. We do the prediction, we do the loss, we find out the loss, we change the gradients, we do the back propagation, do the weights and the biases update, go back again, do the prediction, find the loss, do take the gradients, do the back propagation, and find the weights again. That's a loop that we do, and multiple times we take the loop, we find out that the weights and biases now cannot be moved more. They are at the lowest possible, they are at the best possible rate, where the loss function is the minimum, and that's when we stop this loop, and that's when we say the language model is ready to be used for production use. Now, this is a very simple example that we took over here, but the actual example can be but the actual computation that you see within the chat GPTs or the Anthropics of the world are very strong. So I'll just take a brief pause. Any questions, please let me know, and we'll see you in the next video. Thank you.